Okay, so in the last lecture, I introduced the idea of average velocity and instantaneous velocity. So if d of t is a function which gives the position of an object at time t, then we had a formula for the average velocity between two time points. And we could also compute the instantaneous velocity at a single point by taking the average velocity on a small interval near that point to get an approximation to the instantaneous velocity. Then to get exactly what the speed is at that point, we took the limit as h approaches 0. So when I introduced these concepts, I did it all in the context of a position function, because that's sort of one of the most intuitive examples of this sort of thing, because we have a good idea of what is meant by speed of an object, so it makes sense to talk about average velocity and instantaneous velocity. But in fact, these concepts can... So let's suppose that we now have some arbitrary function of x. We can define similar concepts. So we define the average rate of change of f in essentially exactly the same way as before. So we need 2 points between x equals a and x equals b will be f of b minus f of a divided by b minus a. And we can also define the instantaneous velocity, or in this case instantaneous rate of change, at x equals a is equal to the limit as h approaches 0, f of a plus h minus f of a divided by h. So these things no longer represent a concept of velocity, but they do give us an idea of how quickly the function is changing. So this one here is particularly important. So we have a name for it. So the instantaneous rate of change at x equals a is also known as the derivative of f of x at a, and we denote this by f prime of a, or an equivalent way of writing this is df dx at x equals a. So these are two notations for the same quantity, which is the instantaneous rate of change of the function, which is defined by this limit. By the way, this thing f of a plus h minus f of a over h has shown up a lot, so it's convenient to give that a name. So f of a plus h minus f of a divided by h is what we call a difference quotient. So you'll probably see that referred to in the textbook, and I may use that in lectures as well. So what is the derivative at a point really telling us? Well, if you remember the instantaneous velocity, we could visualize graphically as the slope of a tangent line to the curve. So similarly, if we have a point A here, the derivative at a gives us the slope of this line, which is tangent to the curve. And we call this line the tangent line, as before. And its slope is f prime of a. So once we know the slope, we also know there's one point on the line where it touches the function, so we can use this information to actually figure out what the equation for this tangent line is if we wanted to. So somehow it's telling the derivative at the point A is telling us how quickly the function was going up at that point. If it kept going at the same rate, then it would follow this line, but the rate can change as we move to different points. So over to the left, it's going up more slowly, the tangent line would be more shallow, and over to the right, the graph is going up more steeply, so the derivative would be larger. Another important thing we can notice using the derivative is that since the derivative at a point is the slope of the tangent line, we can say that if f prime of a is positive, that means this line has a positive slope. So that will imply that the function f is increasing at x equals a. So in other words, the graph is going upwards, and similarly, f prime of a less than 0 will tell us that f is decreasing at x equals a. So the derivative can tell us something about how the function is changing and what the graph looks like. So this is useful information. So let's see some examples of how we can calculate derivatives. So let's find the derivative of f of x equals x squared at x equals 2. So to do this, we use our definition of derivative at a point. So f prime of 2 will be equal to the limit as h approaches 0, f of 2 plus h minus f of 2 divided by h. So to calculate this limit, we plug in our 2 plus h and 2 to the formula for f of x. So we get the limit as h approaches 0, 2 plus h squared minus 2 squared divided by h. If we expand this, we get the limit as h approaches 0, 4 plus 4h plus h squared minus 4 divided by h. We can cancel the plus 4 and minus 4 to get the limit as h approaches 0 of 4h plus h squared over h. If we cancel an h from everything and take the limit, then we end up getting 4. So we've seen very similar calculations to this when we were calculating instantaneous velocity, as you may recall. So really, the calculations look exactly the same. It's just that now our function is no longer necessarily representing position. So it's a more generalized notion of rate of change. So let's look at a few more examples, some that we haven't done in previous lectures. So let's try to find the derivative of f of x equals square root of x at x equals 1. So again, the first step is always to use our definition of derivative. So f prime of 1 is equal to the limit as h goes to 0, f of 1 plus h minus f of 1 divided by h. And then the next step is always to plug in what our formula is, in this case square root of x. So we get limit as h goes to 0, square root 1 plus h minus square root 1, all divided by h. So this expression here, we haven't necessarily seen a problem much like this before, so you might be stuck as to what to do. I mean, we can simplify this. Square root of 1 is just 1, but the question is how to simplify this first square root. And it turns out what's useful to do is to rationalize the numerator. Usually we go the other way, you rationalize the denominator to get rid of the square roots in the denominator. But well, since we want to somehow cancel this h in the denominator, we want to get rid of the square roots in the numerator and move them down to the denominator so that we can get something that will allow us to cancel an h. So let's see how that works. We multiply both the top and bottom by square root 1 plus h plus 1. And when we do this, you notice we get square root 1 plus h squared from this first term, which gives us just 1 plus h. Then we get minus square root 1 plus h and plus square root 1 plus h. Those will cancel. And then we get minus 1. So when we simplify this, we get limit as h approaches 0 of 1 plus h minus 1 divided by h times square root 1 plus h plus 1. And now you can see why we wanted to do this, because in the numerator the plus 1 and minus 1 cancel, left over with an h that will cancel with the h in the denominator. So our final answer will be limit as h approaches 0 of 1 over 1 plus square root 1 plus h. And now we can just plug in h equals 0 to get this limit is equal to 1 over 1 plus square root 1, or 1/2. Okay, let's look at one more example. So let's try something slightly different and try to find the equation of the tangent line to f of x equals x cubed at x equals 3. Okay, so we saw when we defined the derivative that the derivative at a point is going to give us exactly the slope of the tangent line at that point. So to find the slope of this line, which we'll need in order to find its equation, we're going to want to find the derivative of this function at x equals 3. So let's do that first. The derivative at 3 is going to be equal to the limit as h approaches 0, x plus 3 cubed minus 3 cubed, all divided by h. Now let's expand this out. There is a quick way to expand a cube, but maybe some of you haven't seen that before, so let's just do it the long way and write this as x plus 3 times x plus 3 squared minus 27 over 8. I forgot the limit as h goes to 0. Now we can expand this square fairly easily, so we get limit as h goes to 0, x plus 3 times x squared plus 6x plus 9 minus 27 all over h. Now we distribute this x plus 3 to everything, so we get an x cubed plus 6x squared plus 3x squared gives us plus 9x squared. Then we have plus 18x plus 9x gives us plus 27x. And then the last term is the 3 times 9, which gives us plus 27. Then we still have the minus 27. I realize I have used x instead of h for some reason, so my apologies. These should all be h's. And then we divide by h. And so these 27s cancel, and then what we're left with all has an h in it, so we can cancel an h from everything. And we're left over with the limit as h approaches 0, h squared plus 9h plus 27. And as h goes to 0, we're left over with just 27. So this tells us the slope of the tangent line at 3 will be equal to 27. Okay, but that's not all the information we need. In order to find the line, we need both the slope and at least one point on the line. So we know that when x equals 3, the tangent line will touch the graph. So we know that 3 comma f of 3 is on the line. And f of 3 is 3 cubed, which gives us 27. So this is our point on the line. And so now we can use the point slope formula to find the equation for the tangent line. So we have y equals mx minus x0 plus y0. M will come from the derivative that we calculated, so the slope is 27. Then the x0 and the y0 come from our points that's on the line, so x0 is 3, y0 is 27. And if you'd like to simplify this, we'll get 27x minus 3 times 27 plus 27 is minus 2 times 27, which is minus 54. So this is our equation for the tangent line. So as you can see, these calculations can get quite tedious. And now imagine I asked you, instead of finding the tangent line of to x cubed at x equals 3, suppose I asked you what's the tangent line at x equals 2. Well, you could follow almost the exact same procedure as I did in this example. But you'd have to replace all the 3's by 2's, and it would be very tedious. So in the next lecture, we'll see a better way to do this so that we don't have to redo this calculation every time we want to change the x value.